You're standing in your backyard on a clear night, gazing up at the stars scattered across the dark sky like diamonds on black velvet. Perhaps you notice Jupiter, shining brightly like a beacon, or glimpse Mars with its subtle reddish glow. They seem so near, don't they? Almost within reach, as if you could pluck them from the sky. But prepare for something that will truly blow your mind. Those points of light you're casually observing represent distances so vast, so unimaginably enormous, that your brain struggles to grasp them. We're not talking about driving to the next city over. We're not even talking about flying to another continent. We're talking about distances that make the entire Earth seem like a grain of sand on an infinite beach. So, just how big is our solar system? And I mean really, truly big. By the end of this journey together, you're going to understand why this question has haunted astronomers for centuries, and why the answer is so mind-bending that it fundamentally changes how you see your place in the universe. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination drift through the solar winds as we uncover truths that will reshape everything you thought you knew. I should warn you, this video might be just too interesting to skip and to consider watching till the end. It might accidentally keep you awake. I'd love to know where you're watching from tonight and what time it is for you. Feel free to drop your location and time in the comments below. Welcome to Stellify Science. Let's begin. Before we dive deep into the cosmic abyss, I want you to do something for me. Think about the farthest you've ever traveled from home. Maybe it's a few hundred miles to visit family. Maybe it's thousands of miles to another country. Hold that distance in your mind, because we're about to put it into a perspective that will make your head spin. Our solar system isn't just big, it's so stupendously, astronomically, ridiculously massive that even using the fastest spacecraft we've ever built, it would take you over 40,000 years just to reach the nearest star beyond our solar neighborhood. And that's traveling at speeds that would circle the entire Earth in about 90 minutes. But here's the thing that's truly captivating. For most of human history, we had no idea. Ancient civilizations looked up at the same sky you see tonight and thought the stars were just tiny lights painted on a celestial dome hovering maybe a few miles above their heads. They had no concept that they were staring into an abyss so deep it defies human comprehension. The journey to understanding our solar system's true scale is one of the most incredible detective stories in human history. It's a tale of brilliant minds who refused to accept what their eyes told them, who dared to measure the unmeasurable, and who discovered that reality is far stranger and more magnificent than anyone ever imagined. Let's start with something that seems simple, but is actually revolutionary. What exactly do we mean when we say solar system? Most people think of the 8 planets orbiting our sun. Maybe throw in some asteroids and comets and call it a day. But that's like describing a vast metropolitan city by only mentioning the downtown skyscrapers, while ignoring all the suburbs, industrial districts, and outlying communities that stretch for hundreds of miles in every direction. Our solar system is more like a cosmic empire, with the sun as the absolute ruler at its center. Its gravitational influence extends so far into space that objects literally trillions of miles away still feel its pull, orbiting around it in vast, slow-motion dances that take thousands of years to complete. Think about this for a moment. When you drop a ball, Earth's gravity pulls it down. That same force, gravity, is what keeps the moon orbiting us. It's what keeps us orbiting the sun. And amazingly, That solar gravitational influence doesn't just stop at Pluto, or even close to it. It reaches out into the cosmic darkness, grabbing hold of icy chunks of rock and frozen gases so far away, they exist in a realm where the sun appears as nothing more than a slightly brighter star among countless others. So when we talk about how big our solar system really is, we're not just measuring the distance to Neptune, or even poor, demoted Pluto. We're measuring the edge of our sun's gravitational kingdom, the boundary where its influence finally weakens enough that other stars can steal away its most distant subjects. But before we venture into those mind-bending outer reaches, let's start our journey closer to home and work our way outward, building up your cosmic perspective one incredible distance at a time. Right now, you're sitting on a planet that's roughly 8,000 miles in diameter. That's pretty big, right? You could fit about 4 Earths lined up side by side across the width of Jupiter. But here's where things start to get interesting. The distance from Earth to our moon is about 240,000 miles. That means you could fit about 30 Earths in the space between us and our closest celestial neighbor. Already we're talking about distances that are hard to visualize. If you could drive to the moon at highway speeds without stopping, it would take you about 4 months of continuous driving to get there. 4 months of driving through empty space to reach that bright disk you can cover with your thumb. But the moon is practically in our backyard compared to what comes next. Our sun sits roughly 93 million miles away from Earth. This distance is so important to astronomy that we use it as a cosmic measuring stick, called an astronomical unit, or AU for short. 1 astronomical unit equals about 93 million miles. To put this in perspective, if Earth were the size of a marble, the sun would be about the size of a large beach ball, positioned about 85 feet away. Even at this scale, we're just getting started with the true immensity of our solar system. Let's take a quick trip through the planetary neighborhood, building up these distances in your mind. Venus, our closest planetary neighbor, comes within about 25 million miles of Earth at its closest approach. That's still about 100 times farther than the Moon. Mars, that rusty red world that captures so much of our imagination, sits anywhere from 35 to 250 million miles away, depending on where both planets are in their orbits. Jupiter, the massive gas giant with its swirling storms and dozens of moons, orbits at an average distance of about 5 astronomical units from the Sun. That's roughly 465 million miles. At this distance, sunlight takes about 43 minutes to travel from our star to Jupiter's cloud tops. Think about that for a second. When you look at Jupiter through a telescope, you're not seeing it as it is right now. You're seeing it as it was nearly 3/4 of an hour ago, because that's how long it took the light to travel across all that empty space to reach your eyes. Saturn, with its magnificent ring system, sits at about 9.5 astronomical units, or roughly 890 million miles from the Sun. The light you see reflecting off Saturn's rings left the Sun about an hour and 20 minutes ago. But here's where our journey starts to get really wild. Uranus, the tilted ice giant rolling along on its side, orbits at about 19 astronomical units from the Sun. That's over 1.5 billion miles. Neptune, the windiest planet in our solar system, sits at about 30 astronomical units, or roughly 2.8 billion miles from our central star. At Neptune's distance, the Sun appears about 900 times dimmer than it does from Earth. If you were standing on Neptune, assuming you could somehow survive the crushing cold and howling winds, the Sun would look like nothing more than a very bright star in an alien sky. And here's the kicker. Even at Neptune's incredible distance of nearly 3 billion miles from the Sun, We're barely scratching the surface of our solar system's true size. Neptune isn't even close to the edge. It's more like we've just walked out of the city center and reached the first ring of suburbs. Beyond Neptune lies a realm that most people have never even heard of. Yet it contains some of the most fascinating and mysterious objects in our entire solar system. This is where we encounter the Kuiper Belt, a vast ring of icy objects that extends from about 30 astronomical units all the way out to around 50 astronomical units from the Sun. Pluto, that beloved former planet, is actually just one resident of this cosmic neighborhood. It orbits at an average distance of about 39 astronomical units, or roughly 3.6 billion miles from the Sun. But Pluto has company out there. Thousands upon thousands of icy worlds drift through this distant realm, most of them too small and too far away for us to see clearly, even with our most powerful telescopes. Some of these Kuiper Belt objects are massive. Eris, one of the objects whose discovery led to Pluto's reclassification, is actually more massive than Pluto and sits at an average distance of about 68 astronomical units from the Sun. That's over 6 billion miles away. At this distance, the Sun provides about as much warmth as a candle would from 2 yards away. These are worlds locked in perpetual winter, where temperatures hover around -400 degrees Fahrenheit. Nitrogen, which makes up most of our atmosphere, is frozen solid at these temperatures. But even the Kuiper Belt, vast as it is, represents only the beginning of our solar system's true extent. Beyond this realm of icy dwarfs lies something even more spectacular and mind-bending. It's a spherical shell of objects so distant they exist in a kind of cosmic deep freeze, barely touched by our sun's warmth or light. This is the Oort Cloud, named after Dutch astronomer Jan Oort, who first proposed its existence. The Oort Cloud is where our solar system's story gets truly incredible, where distances become so large that we have to completely reimagine what we mean when we talk about our cosmic neighborhood. The inner edge of the Oort Cloud begins at roughly 2,000 astronomical units from the Sun. That's about 186 billion miles, but that's just where it starts. The outer edge of the Oort Cloud extends to somewhere between 50,000 and 100,000 astronomical units from the Sun. Let me put that in perspective for you. The outer boundary of our solar system sits roughly 1.5 light years away from the Sun. A light year is the distance light travels in 1 year, moving at the incredible speed of 186,000 miles per second. Even at this cosmic speed limit, it takes light over a year to travel from the Sun to the very edge of its gravitational influence. This means that our solar system is about 3 light years across in total diameter. The nearest star to our Sun, Proxima Centauri, sits just over 4 light years away. In other words, the edge of our solar system is more than halfway to the next star. But here's what's absolutely staggering about these distances. Remember that spacecraft I mentioned earlier? The one that would take 40,000 years to reach the nearest star. That same spacecraft, traveling at about 37,000 miles per hour, would take over 10,000 years just to reach the inner edge of the Oort Cloud. To travel completely across our solar system from one side to the other would take roughly 30,000 years of continuous flight. Human civilization as we know it, from the first cities to the present day, spans only about 10,000 years. Our entire recorded history could pass 3 times over during a single journey across our solar system. And we're not done yet. Because within this vast sphere of gravitational influence, some truly bizarre and wonderful things are happening that challenge everything we think we know about planets, moons, and the nature of our cosmic neighborhood. The Oort Cloud isn't just a collection of random space debris floating in the cosmic void. It's a treasure trove of pristine remnants from the very formation of our solar system. Icy time capsules that have remained virtually unchanged for over 4.5 billion years. These objects are like cosmic fossils, preserving the original materials that swirled around our young sun when the planets were still coming together. What's absolutely mind-blowing is that we've barely scratched the surface of understanding what's actually out there. Scientists estimate that the Oort Cloud contains somewhere between 1 trillion and 100 trillion individual objects. That's more objects than there are stars in our entire galaxy, all bound to our single sun by the invisible threads of gravity. Most of these objects are roughly the size of mountains or small cities, chunks of ice and rock that spend most of their time in the ultimate deep freeze. But occasionally, something disturbs one of these distant wanderers. Maybe it's a passing star whose gravity gives it a gentle nudge. Or perhaps it's the gravitational influence of a massive planet in a neighboring star system. Whatever the cause, some of these icy objects begin the long, slow journey inward toward the sun. This is where things get really spectacular. As these visitors from the outer darkness approach our inner solar system, the sun's heat begins to work its magic. The frozen gases start to sublimate, turning directly from solid to gas without ever becoming liquid. This creates the magnificent tails we see streaking across our night sky. We call these visitors comets, but they're really messengers from the very edge of our solar system, bringing us samples of materials that have been preserved in cosmic storage for billions of years. Some of the most famous comets in history have made this incredible journey. Halley's Comet, which returns every 76 years or so, spends most of its time way out beyond Neptune, taking a leisurely cruise through the outer reaches of our solar system before making its brief, spectacular appearance in our inner neighborhood. But here's something that will absolutely blow your mind. The journey these comets make from the Oort Cloud to the inner solar system can take millions of years. Think about that. A comet might begin its journey toward Earth when our planet is in the middle of an ice age, with massive glaciers covering most of the continents. By the time the comet finally arrives to put on its light show in our sky, entire species have evolved and gone extinct. Continents have shifted, and human civilization has risen from nothing to spacefaring technology. Now, you might be wondering how we know all this stuff about regions of space so distant that no spacecraft has ever visited them. How can scientists be so confident about the existence of the Oort Cloud when we can't even see most of the objects in it? This is where the detective work of astronomy gets really fascinating. It all comes down to the orbits of the comets we can observe. When astronomers plot the paths these cosmic visitors take, they find that many of them are coming from seemingly random directions in space. They're not clustered around the plane where the planets orbit, which is what you'd expect if they originated from the Kuiper Belt. Instead, they arrive from above, below, and all around us, suggesting they're coming from a spherical shell surrounding our entire solar system. By working backward from these orbital paths, scientists can calculate where these comets must have originated. It's like being a detective who finds footprints in the snow and uses them to figure out where the person came from, even if you never actually saw them walking. But the Oort Cloud isn't the only mind-bending aspect of our solar system's size. There are other ways to measure and think about cosmic distances that reveal just how isolated we really are in the vast ocean of space. Consider this perspective. Light from the sun takes about 8 minutes to reach Earth. That means when you step outside on a sunny day, the warmth you feel on your face left the sun's surface 8 minutes ago. It's like having a conversation with someone where every word takes 8 minutes to travel between you. But that 8-minute journey is nothing compared to the time it takes sunlight to reach the outer boundaries of our solar system. Light from the sun takes over 4 hours to reach Neptune. To reach the inner edge of the Oort Cloud, that same light needs over 11 days. To travel completely across our solar system to its farthest boundary would take sunlight roughly 2.5 years. This means that if the sun suddenly went out, we wouldn't know about it for 8 minutes. Neptune wouldn't know for over 4 hours, and the most distant objects in our solar system wouldn't realize their central star had died until over 2 years later. It's like living in a cosmic neighborhood so large that news takes years to travel from house to house. Here's another way to wrap your brain around these distances. If you could shrink our entire solar system down so that the distance from the sun to Neptune fit inside a football field, the nearest star would still be about 4.3 miles away. That's like placing a football field in New York City and having the next nearest football field somewhere in Philadelphia. But perhaps the most humbling way to understand our solar system's size is to think about it in terms of human exploration. We've sent robotic spacecraft to every planet in our solar system, and these mechanical explorers have revealed worlds of incredible beauty and complexity. But even our fastest and most advanced spacecraft move at speeds that make interstellar travel seem almost impossibly slow. Voyager 1, currently our most distant human-made object, has been traveling away from the sun for over 4 decades. It's moving at roughly 38,000 miles per hour, which sounds incredibly fast until you realize that at this speed it would still take over 17,000 years to travel just 1 light year. And remember, our solar system extends roughly 1.5 light years in radius. Voyager 1 has traveled so far that it has actually left the heliosphere, the bubble of charged particles that the sun blows around itself like a cosmic wind. This spacecraft is now traveling through interstellar space, the realm between stars. Yet, it's still technically within our solar system's gravitational influence. It won't escape the sun's gravitational pull completely for another 30,000 years. Think about the implications of this. A spacecraft that has been traveling for longer than most people live, moving faster than any human has ever traveled, still hasn't reached the true edge of our solar system, and won't for hundreds of centuries to come. This is the scale we're dealing with when we talk about our cosmic neighborhood. Distances so vast, they challenge our very ability to comprehend them. Yet this entire system, impossibly large as it seems, is just a tiny speck in the grander scheme of the universe. Size isn't the only mind-bending aspect of our solar system. The sheer variety and strangeness of the worlds contained within this vast realm would seem like science fiction if we didn't have photographs and data proving their existence. We have moons with subsurface oceans that might harbor life, planets where it rains diamonds, worlds with methane lakes and nitrogen snow, and asteroids made almost entirely of precious metals. There are places in our solar system where the sun appears as nothing more than a bright star, where a day lasts longer than a year, where storms larger than our entire planet have been raging for centuries. There are worlds so cold that the atmosphere itself freezes and falls as snow, and others where the surface pressure would crush you instantly, even if you could somehow survive the acid rain. All of this incredible diversity exists within the gravitational embrace of our single star, scattered across distances that make the entire Earth seem like a mote of dust. And we're only just beginning to explore and understand these alien worlds that share our cosmic neighborhood. The more we learn about our solar system's true size and complexity, the more we realize how special and precious our small blue world really is. In all this vast emptiness, spanning light years of space and containing trillions of objects, we know of only one place where life definitely exists, where liquid water flows on the surface, where the temperature and atmospheric conditions are just right for complex chemistry to flourish. We are cosmic lottery winners, living on a planet that sits in just the right place, with just the right conditions, in a solar system that's perfectly arranged to support the incredible complexity we call life. And understanding the true scale of our cosmic home makes this miracle seem even more extraordinary. But our solar system's immensity becomes even more staggering when you consider the speeds at which everything is moving through this vast cosmic arena. Right now, as you sit here, you're not just spinning on Earth's axis at over 1,000 miles per hour, you're also hurtling around the sun at roughly 67,000 miles per hour. That's fast enough to circle the entire Earth in about 22 minutes. Yet, even at these breakneck speeds, it takes our planet an entire year to complete just one orbit around our star. Mars, moving more slowly in its larger orbit, takes nearly 2 Earth years to make the same journey. Jupiter requires almost 12 years. Saturn takes nearly 30 years. And poor Neptune, trudging along in the outer darkness, needs 165 Earth years to complete a single orbit. This means that since Neptune was discovered in 1846, it has completed just over one full orbit around the Sun. Its first observed orbit was completed in 2011, a cosmic marathon spanning multiple human generations. But here's where the scale becomes truly mind-melting. Those orbital speeds that seem so impressive become almost laughably slow when measured against the distances involved. Earth travels roughly 600 million miles during its yearly journey around the Sun. That's like driving around the Earth's equator 24,000 times. Yet, this incredible journey takes place entirely within what we might call the inner suburbs of our solar system. The outer planets are traveling even greater distances with each orbit, but they're moving much more slowly. Neptune crawls along at only about 12,000 miles per hour in its orbit, which sounds fast until you realize that's slower than our fastest spacecraft. At Neptune's orbital speed, it would take over 8 years just to travel the distance between Earth and the Sun once. Now, imagine trying to send a message to someone living on Neptune. Even if we could transmit a signal at the speed of light, the fastest possible speed in the universe, that message would take over 4 hours to reach them. Their reply would take another 4 hours to get back to you. You could start a conversation in the morning and not get a response until dinner time, and that's assuming they replied immediately. But communication delays are just the beginning of the challenges posed by our solar system's enormous scale. Consider what it means for space exploration. When we send commands to a spacecraft orbiting Mars, those instructions can take anywhere from 4 to 24 minutes to arrive, depending on where Mars is in its orbit relative to Earth. This means that when something goes wrong with a Mars mission, there's no real-time remote control from Earth. By the time we see a problem developing and send corrective commands, the spacecraft might have already crashed or moved far from its intended path. Every Mars mission has to be smart enough to handle emergencies on its own, making split-second decisions across hundreds of millions of miles of empty space. The psychological impact of these distances is just as profound. Imagine being an astronaut on a mission to Mars, watching Earth shrink to a pale blue dot and then disappear entirely among the stars. The isolation would be unlike anything humans have ever experienced. You'd be farther from home than anyone in history, in a realm where Earth appears as nothing more than a faint speck of light if it's visible at all, and Mars is relatively close by solar system standards. A mission to Jupiter or Saturn would mean spending years in the cosmic wilderness, so far from Earth that radio signals would take nearly an hour and a half to make the round trip. You could ask Mission Control a question and literally take a nap before receiving an answer. But perhaps the most humbling aspect of our solar system's scale is how it reveals our cosmic insignificance while simultaneously highlighting our incredible uniqueness. In all this vast emptiness, across trillions of cubic miles of space, across distances that light itself takes years to traverse, we know of only one tiny oasis where life has taken hold and flourished. The numbers are almost incomprehensible. Our solar system is roughly 99.8% empty space. If you could somehow remove all that emptiness and pack together just the solid matter from all the planets, moons, asteroids, and comets, the resulting ball would be smaller than our sun. And the sun itself, massive as it is, would be lost like a grain of sand in the vastness of the space it illuminates. Yet within this seemingly barren immensity, we find worlds of breathtaking beauty and complexity. Europa, one of Jupiter's moons, likely contains more liquid water beneath its icy surface than all of Earth's oceans combined. Titan, Saturn's largest moon, has lakes and rivers of liquid methane flowing across its surface under a thick orange atmosphere. Enceladus shoots geysers of water ice into space from its south pole, creating one of Saturn's rings from its own subsurface ocean. Each of these worlds represents a unique experiment in planetary science, a different answer to the question of what happens when gravity, chemistry, and time interact under varying conditions. Some are frozen wastelands where the air itself would freeze solid. Others are pressure cookers, where lead would melt and flow like water. Still others might harbor the ingredients for life in hidden oceans beneath miles of ice. The diversity is staggering, and it exists across distances that make these worlds more isolated from each other than any places on Earth have ever been. The gap between Jupiter's moons is larger than the distance between Earth and our moon. The space between Saturn's major moons dwarfs the distance between continents on our planet. This isolation has allowed each world to evolve its own unique characteristics over billions of years. Unlike Earth, where weather systems and ocean currents eventually mix and homogenize conditions around the globe, these distant worlds have developed in cosmic solitude, creating environments so alien that they challenge our very understanding of what a planet can be. Consider Uranus, that strange world rolling on its side like a cosmic bowling ball. Something in its distant past, perhaps a collision with another planet-sized object, knocked it over so that its axis of rotation is tilted 98 degrees from vertical. This means that Uranus experiences seasons lasting 21 Earth years, with each pole alternately facing the sun for decades at a time, while the other hemisphere endures decades of darkness. Or think about Venus, Earth's so-called twin, where the greenhouse effect has run completely out of control. The surface temperature is hot enough to melt lead, the atmospheric pressure is crushing, and it rains sulfuric acid. This hellish world sits just 25 million miles away from us at its closest approach. Yet it might as well be in another universe for all the similarity it bears to our temperate, life-friendly planet. These extreme variations exist within our single solar system, bound together by the gravity of one star, yet separated by distances so vast that each world has become a unique laboratory for planetary physics and chemistry. The isolation imposed by space has allowed each planet and major moon to write its own story, to explore its own evolutionary path without interference from its neighbors. And we're still discovering new chapters in these stories. In recent decades, our robotic explorers have revealed that several moons in the outer solar system likely contain more liquid water than Earth. They found organic compounds, the building blocks of life, scattered throughout the solar system. They've detected seasonal changes on worlds billions of miles from the sun, and discovered that even in the coldest, most distant regions of our cosmic neighborhood, dynamic processes are still shaping planetary surfaces. The scale of our solar system means that we're essentially exploring multiple alien worlds, each as complex and varied as Earth itself, scattered across a volume of space so large that it defies human intuition. Every new mission reveals surprises that force us to reconsider what we thought we knew about planetary science, about the conditions necessary for life, and about the incredible diversity of worlds that can exist around a single star. But as vast as our solar system appears from our earthbound perspective, it represents just the tiniest fraction of the cosmic story. The distances we've been exploring, as mind-bendingly large as they seem, are nothing compared to the spaces between stars, between galaxies, between the largest structures in the universe. Our entire solar system, from the Sun to the farthest reaches of the Oort Cloud, could fit comfortably within the space between our Sun and the nearest star. All of this incredible diversity, all of these alien worlds and cosmic phenomena we've been discussing, exist within what amounts to a tiny bubble in the vast ocean of interstellar space. The nearest star system, Alpha Centauri, contains at least 3 stars and potentially several planets. Yet the gap between our solar system and theirs is so enormous that it would take our fastest spacecraft tens of thousands of years to cross it. The distances we measure within our solar system, in astronomical units, would need to be measured in light years when we start talking about interstellar space. And even that represents just the beginning of cosmic scale. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars, most of them likely surrounded by their own planetary systems. The distances between these stars are so vast that if you could somehow travel at the speed of light, it would take you 100,000 years to cross from one side of our galaxy to the other. Yet, our galaxy is just one of trillions in the observable universe, separated by distances that make the space between stars look cramped by comparison. The nearest major galaxy to ours, Andromeda, sits over 2.5 million light-years away. Light that left Andromeda when our earliest human ancestors were learning to use tools is just now reaching Earth. This cosmic perspective makes our solar system seem almost cozy by comparison. Yet, it also highlights just how special and rare our little corner of the universe might be. In all the vast emptiness of space, across distances that challenge the very limits of human comprehension, we find ourselves in this one perfect spot where conditions are just right for liquid water, for complex chemistry, for the incredible phenomenon we call life. The more we understand about our solar system's true scale, the more we appreciate both our cosmic insignificance and our incredible good fortune. We are temporary arrangements of atoms that have somehow become conscious enough to contemplate the very vastness that contains us. Living on a tiny world in a vast system that is itself a mere speck in an almost infinite universe. Yet within this seemingly impossible scale, something truly extraordinary is happening right now that makes our solar system even more remarkable than its sheer size alone would suggest. As we speak, our entire cosmic neighborhood is moving through space at speeds that would make your head spin, carrying us on a journey through the galaxy that spans distances so vast they make even our solar system's dimensions seem quaint. Right now, our Sun, along with all its planets, moons, asteroids, and comets, is racing through the Milky Way galaxy at roughly 500,000 miles per hour. That's fast enough to circle the Earth in about 3 minutes. Yet, even at this breakneck pace, it takes our solar system approximately 225 million years to complete just one orbit around the center of our galaxy. Think about that timeline for a moment. The last time our solar system was in this exact position in the galaxy, dinosaurs ruled the Earth. The next time we complete this cosmic circuit, our sun will be noticeably older and dimmer. And who knows what form life on Earth might have taken, if it still exists at all. But our galactic journey is just one layer of motion in this cosmic ballet. Our entire galaxy is also moving, racing through the universe toward a collision with the Andromeda galaxy that won't occur for another 4.5 billion years. When that cosmic crash finally happens, the combined gravitational forces will completely reshape both galaxies, flinging stars into new orbits and potentially ejecting our solar system into the lonely depths of intergalactic space. Even more mind-bending is the realization that space itself is expanding. The very fabric of the universe is stretching, carrying galaxies away from each other, at speeds that increase with distance. This means that the most distant objects we can observe are racing away from us faster than the speed of light. Not because they're moving through space that quickly, but because space itself is expanding between us. This cosmic expansion has a profound effect on how we measure distances in our universe and raises fascinating questions about what lies beyond the edge of our solar system. As space expands, the gravitational influence of our sun becomes relatively weaker compared to the expansion of the universe itself. This suggests that there might be an absolute outer boundary to our solar system, beyond which objects would be swept away by cosmic expansion rather than held in solar orbit. Scientists estimate this boundary might lie somewhere around 100,000 astronomical units from the Sun, roughly where we think the outer edge of the Oort Cloud exists. This isn't a coincidence. The edge of our solar system might literally be defined by the point where our Sun's gravity can no longer compete with the expansion of space itself. But here's something that will absolutely scramble your brain. The expansion of space means that objects at the very edge of our solar system are slowly but constantly drifting away from the Sun. Over cosmic timescales, our solar system is actually shrinking as its most distant members are gradually stolen away by the expanding universe. This process is so slow that it's essentially imperceptible on human timescales. It would take trillions of years for this expansion to have any noticeable effect on even the outer reaches of the Oort Cloud. But the fact that it's happening at all reveals something profound about the nature of our cosmic neighborhood and its place in the larger universe. Our solar system isn't a static, unchanging structure frozen in space and time. It's a dynamic, evolving system that's constantly responding to forces both internal and external. Planets migrate inward and outward over millions of years due to gravitational interactions. The Sun gradually grows brighter as it ages, slowly pushing the habitable zone outward. Passing stars occasionally disturb the Oort Cloud, sending showers of comets racing toward the inner solar system. Even the shape of our solar system changes over time. The orbits of the planets aren't perfectly stable circles, but complex ellipses that shift and wobble due to mutual gravitational influences. These orbital variations occur over such long timescales that they're invisible to human observation, but they're profound enough to affect climate patterns on Earth over hundreds of thousands of years. Jupiter, our solar system's gravitational giant, acts like a cosmic shepherd, using its massive gravity to protect the inner planets from asteroid and comet impacts, while simultaneously stirring up the asteroid belt and occasionally flinging dangerous objects toward Earth. Without Jupiter's protective influence, life on Earth might never have had the stable conditions necessary to evolve complex forms. But Jupiter's protection comes with a price. Its gravitational influence also prevents the asteroid belt from coalescing into a proper planet. The combined mass of all asteroids in the belt is less than that of our moon, scattered across a region of space larger than the orbit of Mars. These rocky fragments represent the building materials for a world that never was, prevented from forming by Jupiter's overwhelming gravitational dominance. This gravitational choreography extends throughout our solar system, creating resonances and patterns that govern the motion of countless objects. Some asteroids are locked in orbital resonances with Jupiter, completing exactly 2 orbits for every one Jupiter completes, or 3 orbits for every 2. These mathematical relationships create gaps in the asteroid belt, where objects simply cannot maintain stable orbits. Similar resonances exist throughout the outer solar system. Pluto is locked in a 2 to 3 resonance with Neptune, meaning it completes exactly 2 orbits for every 3 that Neptune completes. This gravitational partnership has kept Pluto's orbit stable for billions of years, despite the fact that their orbital paths actually cross when viewed from above. The more we study these gravitational relationships, the more we realize that our solar system is less like a collection of independent objects orbiting the Sun and more like a single, integrated system, where every component influences every other component. Change the mass or orbit of any major planet, and the effects would ripple throughout the entire system, potentially destabilizing orbits and sending planets careening into new paths. This interconnectedness becomes even more remarkable when you consider the timescales involved. The gravitational influence of Jupiter on Earth's orbit operates over cycles lasting hundreds of thousands of years. These tiny orbital variations help drive ice ages and other long-term climate changes on our planet. The gravitational dance between Earth and the Moon gradually slows our planet's rotation while pushing the Moon slowly away from us. In the early days of our solar system, the Moon was much closer to Earth, and our planet spun much faster. A day lasted only about 6 hours, and the Moon appeared enormous in our sky, creating tides that would have been catastrophically large by today's standards. Over billions of years, tidal friction has gradually slowed Earth's rotation and pushed the Moon to its current distance of about 240,000 miles. This process continues today. The Moon is still slowly spiraling away from Earth at about 1.5 inches per year. In the distant future, assuming no other catastrophes intervene, the Moon will be so far away that it will no longer be able to create total solar eclipses. The remarkable cosmic coincidence that makes the Moon appear almost exactly the same size as the Sun in our sky is temporary, existing only during this brief moment in cosmic history. These ongoing changes remind us that the solar system we observe today is just a snapshot of a continuously evolving system. The distances we measure, the orbital periods we calculate, the relationships between objects that seem so permanent and stable are all slowly shifting on timescales that dwarf human civilization. 4.5 billion years ago, when our solar system was young, the arrangement of planets was quite different from what we see today. Jupiter and Saturn likely migrated inward toward the Sun before being pulled back outward by their gravitational interaction with each other. This migration may have scattered the original asteroid belt and disrupted the formation of planets in the inner solar system. Some scientists think there may have been additional planets in the early solar system that were ejected into interstellar space during these chaotic rearrangements. These rogue planets, if they exist, would now be wandering through the galaxy as cosmic orphans, no longer bound to any star. Recent astronomical surveys have begun to detect objects that might be these ejected worlds, dark and cold remnants of planetary systems that once were. The scale of these processes, both in terms of distance and time, challenges our ability to comprehend the true nature of our cosmic neighborhood. We're not just living in a large solar system. We're living in an ancient, dynamic system that has been evolving for billions of years and will continue evolving for billions more. Our perspective on this evolution is incredibly limited. Human civilization spans perhaps 10,000 years. Written history covers only a few thousand years. Even our most advanced astronomical observations extend back only a few centuries. Yet the processes that shape our solar system operate over timescales of millions and billions of years. It's like trying to understand the flow of a river by observing a single drop of water for a microsecond. We can see the immediate motion, but we miss the larger currents, the seasonal variations, the long-term changes in the river's course. Our view of the solar system is similarly constrained by our brief existence within it. But here's what makes this limitation both humbling and inspiring. Despite existing for such a tiny fraction of our solar system's history, despite being confined to a single planet in this vast cosmic arena, we've managed to piece together the story of our solar system's formation, evolution, and ultimate fate. We've sent robotic explorers to every major planet, mapped the orbits of thousands of asteroids and comets, and detected planets orbiting distant stars. This achievement becomes even more remarkable when you consider the scale we're dealing with. We've managed to study objects billions of miles away using instruments that fit in our hands. We've calculated the masses of planets by observing how they affect the motion of their moons. We've determined the composition of distant worlds by analyzing the light they reflect or emit. Every measurement, every observation, every calculation represents a triumph of human ingenuity over the vast distances that separate us from the objects we study. When we look at Saturn's rings through a telescope, we're gathering light that has traveled for over an hour through empty space to reach us. When we receive data from a spacecraft at Jupiter, those radio signals have crossed 400 million miles of vacuum. The fact that we can study our solar system at all, given its enormous scale and our tiny size within it, is perhaps as remarkable as any of the discoveries we've made. We are cosmic detectives, piecing together clues from across billions of miles of space and billions of years of time, gradually building a picture of our place in this vast system. And that picture keeps getting more complex and more beautiful with every new discovery. Recent missions have revealed that several moons in the outer solar system contain subsurface oceans that might harbor life. We've discovered that even small asteroids can have their own tiny moons. We've found that the space between planets isn't empty but filled with dust, charged particles, and magnetic fields that create invisible highways and barriers throughout our solar system. Each new revelation adds another layer to our understanding of just how intricate and interconnected this vast system really is. The distances that once seemed like empty voids are actually filled with subtle influences and hidden relationships. The objects that appear as simple points of light in our telescopes turn out to be complex worlds with their own weather, geology, and unique characteristics. Our solar system isn't just big, it's not just old, it's not just complex, it's all of these things simultaneously, operating on scales of distance, time, and intricacy that push the very limits of human comprehension, and we've only just begun to explore it. The sheer magnitude of what we're dealing with becomes even more staggering when you realize that everything we've discussed so far represents just the objects we know about. The truth is, our solar system is filled with countless objects that remain completely invisible to us, hidden in the cosmic darkness beyond the reach of even our most powerful telescopes. Consider this mind-bending fact. For every asteroid we've discovered and cataloged, there are likely thousands more that we haven't detected yet. The asteroid belt alone probably contains over 1 million objects larger than half a mile across, and millions more smaller fragments that we'll never be able to track individually. Each of these represents a potential world in miniature, with its own unique composition, rotation, and orbital characteristics. But asteroids are just the beginning. Throughout the Kuiper Belt and scattered disk, there are likely tens of thousands of objects larger than 60 miles across that we haven't discovered yet. Some of these undiscovered worlds might be larger than some of the moons we know about. They're out there right now, silently orbiting in the darkness, waiting for our technology to advance enough to spot them. The Oort Cloud presents an even more extreme case of cosmic hide-and-seek. Remember those trillions of objects I mentioned earlier? We've directly observed maybe a few dozen of them, and only when they venture close enough to the sun to develop visible tails as comets. The vast majority of Oort Cloud objects remain completely invisible to us, too small and too distant to reflect enough sunlight for our telescopes to detect. This means that our solar system is far more populous than we can currently observe. It's like trying to estimate the population of a vast city at night when most of the buildings have their lights turned off. You can see the bright downtown core and a few scattered neighborhoods, but the majority of the urban landscape remains hidden in darkness. What makes this even more fascinating is that we're discovering new objects all the time, and each discovery forces us to revise our understanding of our solar system's structure and history. In recent decades, we've found objects in the outer solar system that don't fit neatly into our existing categories. Some follow highly elliptical orbits that take them far beyond Pluto before swinging back toward the sun. Others seem to be influenced by gravitational forces that we can't fully explain. These discoveries have led some scientists to propose the existence of additional planets in our solar system, worlds so distant and dim that we haven't detected them yet. The hypothetical Planet 9, if it exists, would orbit somewhere between 200 and 1,000 astronomical units from the Sun. That's so far away that it would receive almost no heat from our star, existing in a perpetual deep freeze where temperatures hover near absolute zero. Finding such an object would be like trying to spot a black marble rolling around in a football stadium with only a penlight for illumination. It might be out there right now, following its slow, stately orbit through the outer darkness, completely invisible to our current technology, but gradually revealing its presence through its gravitational influence on other objects. The search for these hidden worlds represents one of the most exciting frontiers in solar system exploration. Every few months, automated sky surveys discover new objects in the outer reaches of our cosmic neighborhood. Some turn out to be relatively ordinary chunks of ice and rock, but others surprise us with unusual characteristics that challenge our understanding of how planets and small bodies form and evolve. The process of discovery itself reveals just how vast the search space really is. Astronomers have to examine millions of images, looking for tiny points of light that move slowly against the background of distant stars. It's incredibly tedious work, like looking for a specific grain of sand on a beach. But the payoff can be revolutionary. When we do find these distant objects, studying them presents its own set of challenges. They're so far away that even our largest telescopes can barely make them out as more than points of light. Determining their size, composition, and orbital characteristics requires years of careful observation and sophisticated analysis. But here's what's truly remarkable about these discoveries. Each new object we find adds another piece to the puzzle of our solar system's formation and evolution. These distant worlds are like cosmic fossils, preserving information about the conditions that existed when our solar system was young. They're time capsules from an era when the planets were still forming and the architecture of our cosmic neighborhood was being established. The more we discover about these outer realms, the more we realize that our solar system's influence extends even farther than we previously thought. Some of the most distant objects we've found are still clearly bound to our sun's gravity, following orbits that take thousands of years to complete. This suggests that our solar system's gravitational reach might extend even beyond the traditional boundaries of the Oort Cloud. Think about what this means for our understanding of cosmic distances. We're not just dealing with a solar system that's a few light years across. We're potentially looking at a region of space where our sun's influence can be detected across distances that approach the nearest neighboring star systems. The boundary between what belongs to our solar system and what belongs to interstellar space becomes increasingly blurry the farther out we look. This blurring of boundaries reflects a deeper truth about the nature of space itself. The universe isn't neatly divided into separate, isolated systems. Instead, it's a continuous web of gravitational influences, magnetic fields, and particle flows that connect everything to everything else across vast distances. Our solar system exists within this larger cosmic environment, influenced by and influencing its surroundings in ways we're only beginning to understand. The passage of nearby stars can disturb the Oort Cloud, sending showers of comets racing toward the inner solar system. Interstellar dust and gas flow through our cosmic neighborhood, subtly affecting the orbits of our most distant objects. Even more fascinating is the realization that our solar system is currently passing through what astronomers call the local bubble, a region of space that's been carved out by ancient supernova explosions. This bubble of hot, thin gas extends for hundreds of light years in all directions, and our solar system has been traveling through it for several million years. The local bubble affects our solar system in subtle but measurable ways. It influences the flow of cosmic rays that reach our planets, affects the density of interstellar material in our neighborhood, and even plays a role in the long-term climate patterns on Earth. We're not just isolated observers of the universe. We're active participants in cosmic processes that span galactic distances and timescales. This cosmic context makes our solar system's already impressive dimensions seem even more remarkable. We're not just dealing with a large collection of objects orbiting a single star. We're looking at a complex, dynamic system that interacts with its galactic environment across multiple scales of distance and time. The heliosphere, that bubble of charged particles blown out by our sun, extends roughly 100 astronomical units in all directions. This might sound small compared to the Oort Cloud, but it represents our solar system's most direct interaction with the interstellar medium. Where the solar wind meets the interstellar wind, complex physics creates shock waves and boundary layers that affect everything, from cosmic ray penetration to the behavior of interstellar dust. Voyager 1 and Voyager 2, our most distant robotic explorers, have crossed this boundary and are now sending back our first direct measurements of the interstellar environment. What they found is that the space between stars isn't empty or uniform. It's filled with magnetic fields, charged particles, and structures that reveal the complex history of stellar explosions, stellar winds, and galactic processes that have shaped our cosmic neighborhood over millions of years. These discoveries are rewriting our understanding of where our solar system ends and interstellar space begins. The traditional view of a clear boundary is giving way to a more nuanced picture of overlapping zones of influence that extend across multiple light years. Our solar system doesn't have a sharp edge. Instead, it gradually transitions into the larger galactic environment through a series of complex boundary regions. But perhaps the most mind-bending aspect of our solar system's scale is how it relates to time itself. The distances we've been discussing aren't just measurements of space. They're also measurements of time. Light from the sun takes over 2 years to reach the outer edge of the Oort Cloud, which means that the most distant parts of our solar system exist in a different temporal relationship with our star than we do. If something dramatic happened to the sun right now, we'd know about it in 8 minutes. But the most distant objects in our solar system wouldn't be affected for over 2 years. In a very real sense, different parts of our solar system exist in different moments of solar time, separated not just by distance but by the finite speed of light itself. This temporal aspect of solar system distances becomes even more striking when you consider orbital periods. Objects in the inner solar system complete their orbits in months or years, while objects in the Oort Cloud might take millions of years to complete a single journey around the sun. Some of the comets we observe today began their inward journey when early human ancestors were just learning to use stone tools. The scale of these temporal relationships challenges our intuitive understanding of what it means for objects to be part of the same system. Can we really say that a comet with a million-year orbital period is part of the same solar system as Earth, which completes its orbit in just 1 year? In what sense do these objects share a common present when their relationship with the sun operates on such vastly different timescales? These questions touch on deep philosophical issues about the nature of time and causality in cosmic systems. Our solar system isn't just large in space, it's large in time, encompassing processes and relationships that operate across multiple scales of temporal experience. The formation of our solar system itself took place over millions of years, a process so gradual that no single moment can be identified as the instant when it came into being. The gravitational collapse of the original solar nebula, the accretion of planetesimals into planets, the migration of giant planets to their current orbits, the late heavy bombardment that scarred the inner planets, all of these processes unfolded over timescales that dwarf human comprehension. Yet here we are, temporary arrangements of matter that have achieved consciousness just long enough to contemplate the vast system that contains us. We exist for what amounts to an instant in solar system time. Yet, we've managed to piece together the story of our cosmic home's 4.5 billion year history. This achievement becomes even more remarkable when you consider that we're not just studying our solar system from within it. We're studying it while moving through it at tremendous speeds. As I mentioned earlier, we're racing around the sun at 67,000 miles per hour, while the sun itself hurtles through the galaxy at 500,000 miles per hour. We're conducting our observations from a platform that's constantly in motion through the very system we're trying to understand. It's like trying to map a vast city while riding on a speeding train that never stops. The perspective is constantly shifting. Distances and angles are always changing, and you can never step outside the system to get an objective, stationary view of the whole thing. Yet somehow, through careful observation and mathematical analysis, we've managed to create accurate maps of our cosmic neighborhood and understand how all its components fit together. The technology that makes this possible is itself a testament to human ingenuity in the face of cosmic scale. Our most powerful telescopes can detect objects billions of times fainter than what the naked eye can see. Our spacecraft navigation systems can plot courses across billions of miles with accuracy measured in kilometers. Our mathematical models can predict the positions of planets centuries into the future with remarkable precision. But even our most advanced technology is humbled by the sheer scale of what we're trying to study. The James Webb Space Telescope, humanity's most powerful space-based observatory, can peer deeper into the universe than ever before. Yet it still can't resolve individual objects in the Oort Cloud. The Voyager spacecraft, our most distant emissaries, have been traveling for over 4 decades and are still within our solar system's gravitational influence. These limitations remind us that despite all our technological achievements, we're still dealing with distances and timescales that challenge the very limits of what's possible to observe and understand. We're cosmic detectives, working with incomplete evidence, trying to reconstruct the story of our solar system from the limited clues we can gather. Yet, the picture that emerges from this detective work is breathtaking in its scope and beauty. Our solar system isn't just a collection of objects scattered through empty space. It's an integrated, dynamic system where every component influences every other component across vast distances and long timescales. It's a cosmic ecosystem where the movement of planets affects asteroid orbits, where the solar wind shapes the magnetic environments of distant moons, where the passage of nearby stars can trigger comet showers that rain down on the inner planets. The more we learn about our solar system's true scale and complexity, the more we appreciate what an extraordinary place we call home. In all this vast emptiness, across all these mind-bending distances, in all this cosmic time, we find ourselves on a small blue world that happens to exist in just the right place, under just the right conditions, for liquid water to flow and complex chemistry to flourish. The odds against this seem almost impossibly small. Yet here we are, conscious beings who have emerged from this cosmic dance of gravity, chemistry, and time, capable of contemplating the very system that gave birth to us. We are the universe becoming aware of itself, temporary patterns of matter and energy that have learned to measure cosmic distances and ponder their own origins. And this brings us to perhaps the most mind-bending realization of all. When we talk about measuring our solar system, we're not just dealing with static distances frozen in space like mile markers on a cosmic highway. Every single measurement we make is constantly changing because nothing in our solar system ever stands still. Right now, as you absorb these cosmic dimensions, Mars is either racing toward Earth at roughly 15,000 miles per hour or speeding away from us at the same rate, depending on where we both happen to be in our respective orbits. Jupiter is lumbering along its massive orbital path, but even its seemingly slow motion carries it at over 29,000 miles per hour through the void. This constant motion creates what astronomers call the dynamic geometry of space. The distance between any two objects in our solar system is never the same from one moment to the next. When mission planners calculate trajectories for spacecraft, they're not just plotting a course through space, they're choreographing a dance through four-dimensional spacetime, timing arrivals to intercept moving targets across billions of miles of constantly shifting cosmic real estate. Consider what this means for something as simple as measuring the distance to Pluto. When Pluto is at its closest approach to the Sun, it sits roughly 2.8 billion miles from Earth. But when it swings out to the farthest point in its highly elliptical orbit, that distance can increase to over 4.6 billion miles. That's like having your neighbor's house sometimes be down the street and sometimes be in another state. all while you're trying to give someone directions. But Pluto's wandering is nothing compared to the truly extreme objects lurking in the outer darkness of our solar system. Some of these distant wanderers follow orbits so stretched and elongated that they spend most of their time in the cosmic equivalent of Antarctica, only occasionally swooping close enough to the sun to warm up above the temperature of liquid nitrogen. Take Sedna, one of the most distant objects we've discovered in our solar system. At its closest approach to the sun, Sedna comes within about 76 astronomical units, which sounds close until you realize that's still over 7 billion miles away, more than twice Neptune's distance. But when Sedna reaches the far end of its incredibly elongated orbit, it travels out to roughly 937 astronomical units from the sun. That's over 87 billion miles, so far away that the sun would appear as nothing more than a slightly brighter star in a sky full of stars. Sedna takes approximately 11,400 years to complete just one orbit around the sun. Think about that timeline. The last time Sedna was at its current position, humans were just emerging from the last ice age, developing agriculture, and building the first permanent settlements. The next time it returns to the same spot, our civilization will likely be unrecognizable, assuming it still exists at all. But here's what makes Sedna truly extraordinary. Its orbit is so distant and so stretched that something must have gravitationally nudged it into this bizarre trajectory. The sun alone couldn't have created such an extreme orbital path. This suggests that either a passing star disturbed Sedna's orbit long ago, or there's another massive object in our outer solar system that we haven't discovered yet. This brings us to one of the most tantalizing mysteries currently haunting astronomy. Multiple lines of evidence suggest there might be an undiscovered planet lurking in the far reaches of our solar system, something astronomers have dubbed Planet 9. If it exists, this world would be roughly the size of Neptune, orbiting somewhere between 200 and 1,200 astronomical units from the sun. At those distances, Planet 9 would be so cold and so dim that finding it would be like trying to spot a charcoal briquette floating in the darkness of a football stadium. It would receive so little heat from the sun that its surface temperature would hover around negative 370 degrees Fahrenheit, cold enough to freeze nitrogen solid. The search for Planet 9 represents one of the most challenging treasure hunts in scientific history. Astronomers are essentially looking for a needle in a cosmic haystack, scanning millions of square degrees of sky for an object that might move less than the width of a human hair, as seen from a mile away over the course of an entire year. But the potential discovery of Planet 9 would revolutionize our understanding of our solar system's size and structure. It would push our cosmic neighborhood's confirmed boundaries out to distances that begin to approach interstellar scales. We'd be dealing with a planetary system that spans roughly 1% of the distance to the nearest star, a realm so vast that radio signals would take over 5 days to travel from the sun to this distant world. Communication with any spacecraft we might eventually send to Planet 9 would require the patience of geological time. A simple message from Earth would take days to arrive, and the response would take days to return. You could ask a question and not receive an answer for a week. But even Planet 9, if it exists, might not represent the true edge of our solar system's gravitational influence. Recent computer simulations suggest that objects as far out as 150,000 astronomical units might still be gravitationally bound to our sun. That's roughly 2.5 light years away, more than halfway to the nearest star. At these distances, we're dealing with a realm where the very concept of belonging to our solar system becomes almost philosophical. Objects this far out would take millions of years to orbit the sun once. They would be more influenced by passing stars and galactic tides than by our own star. Yet, mathematically, they would still be part of our cosmic family, however tenuous that relationship might be. This extreme outer boundary reveals something profound about the nature of gravitational influence in the universe. Gravity never truly reaches zero. No matter how far you travel from a massive object, it just gets weaker and weaker, following what mathematicians call an inverse square law. Double the distance, and the gravitational pull becomes 4 times weaker. Triple the distance, and it becomes 9 times weaker. But weaker doesn't mean gone. Even at the incredible distance of 150,000 astronomical units, our sun's gravity would still be detectable, still capable of holding objects in orbit, still defining the boundary between what belongs to us and what belongs to the galaxy at large. This fading influence creates what astronomers call the Hill sphere, the region around any massive object where its gravity dominates over all other gravitational influences. For our sun, this Hill sphere extends roughly 2 light years in all directions, creating a sphere of gravitational dominance that's actually larger than the distance to our nearest stellar neighbors. The implications are staggering. Our solar system's gravitational territory actually overlaps with the territories of nearby star systems. There might be objects in space that feel gravitational tugs from multiple stars simultaneously, cosmic orphans that aren't quite sure which stellar family they belong to. This overlap zone between stellar gravitational territories represents one of the most mysterious regions in our local galactic neighborhood. It's a realm where the normal rules of planetary dynamics break down, where objects might be captured by one star system, then stolen away by another, as stellar positions shift over millions of years. Some scientists speculate that this disputed territory might be populated by rogue planets, worlds that were ejected from their birth star systems during chaotic formation processes. These cosmic wanderers would drift through interstellar space, occasionally being captured by passing stars or settling into long-term orbits in the gravitational borderlands between stellar systems. If such rogue planets exist in the outer reaches of our solar system, they would represent the ultimate expression of cosmic scale. These would be worlds that have traveled interstellar distances, carrying with them the chemical signatures and formation history of alien star systems. Studying them would be like examining cosmic fossils from distant regions of our galaxy. But the search for such exotic objects pushes our observational capabilities to their absolute limits. These hypothetical rogue planets would be virtually invisible, emitting no light of their own and reflecting almost no sunlight due to their enormous distances. Detecting them would require next-generation telescopes and survey techniques that don't yet exist. Yet the search continues, driven by the tantalizing possibility that our solar system might be far stranger and more complex than we currently imagine. Each new discovery in the outer darkness reveals that our cosmic neighborhood contains secrets we're only beginning to uncover. The Kuiper Belt, once thought to be a relatively simple disk of icy debris, has turned out to be a complex region with distinct populations of objects following different types of orbits. Some Kuiper Belt objects have nearly circular paths around the sun, while others follow highly elongated trajectories that carry them far beyond Pluto before swinging back toward the inner solar system. This diversity suggests a violent and chaotic past, a time when gravitational interactions between the giant planets scattered objects throughout the outer solar system like cosmic billiard balls. Computer simulations of these early dynamics reveal a solar system in constant upheaval, with planets migrating inward and outward, asteroid belts being disrupted and reformed, and countless small bodies being flung into interstellar space or crashed into planetary surfaces. The scars of this chaotic period are still visible throughout our solar system. The heavily cratered surfaces of the Moon and Mercury record the tail end of this cosmic bombardment. The unusual tilts and spins of Uranus and Venus hint at massive collisions that knock these worlds off their original axes. Even the asteroid belt between Mars and Jupiter represents the shattered remains of planetary building materials that never quite managed to coalesce into a proper world. But perhaps the most dramatic evidence of our solar system's violent past lies in the late heavy bombardment, a period roughly 4 billion years ago, when the inner planets were pelted by an intense shower of asteroids and comets. This cosmic storm may have been triggered by the migration of Jupiter and Saturn to their current orbits, a gravitational reshuffling that sent waves of debris cascading throughout the solar system. The timing of this bombardment coincides remarkably with the earliest evidence of life on Earth, suggesting that the same cosmic violence that scarred planetary surfaces might have also delivered the water and organic compounds necessary for biology to take hold. In a very real sense, the enormous scale and dynamic history of our solar system may have been essential for creating the conditions that allowed life to emerge on our small blue world. This connection between cosmic scale and biological possibility extends far beyond Earth. Several moons in the outer solar system, particularly Europa, Enceladus, and Titan, show evidence of subsurface oceans that might harbor life. These hidden seas exist because of tidal heating, a process where gravitational interactions with massive planets generate enough internal friction to keep water liquid, despite surface temperatures that would freeze carbon dioxide solid. The fact that these potentially habitable environments exist in the outer reaches of our solar system, billions of miles from the sun's warmth, reveals how the sheer size and gravitational complexity of our cosmic neighborhood create opportunities for life in places we never expected. The scale that once seemed like an obstacle to habitability might actually be one of its greatest enablers. But even these remarkable discoveries pale in comparison to the most profound implication of our solar system's true size. The distances we've been exploring represent just the beginning of an even grander cosmic perspective. Our entire solar system, vast as it appears from our earthbound viewpoint, occupies only the tiniest fraction of our galaxy's volume. The Milky Way contains somewhere between 200 and 400 billion stars, most of them likely surrounded by their own planetary systems. If every star system were roughly the same size as ours, and if they were packed as efficiently as possible, with no empty space between them, our entire galaxy would still be more than 99% empty space. But star systems aren't packed efficiently at all. They're separated by vast gulfs of interstellar vacuum that dwarf even the enormous distances within individual solar systems. The space between our sun and the nearest star contains virtually nothing except incredibly thin wisps of interstellar gas and dust, magnetic fields so weak they barely register on our most sensitive instruments, and the occasional lonely rogue planet drifting through the cosmic void. This interstellar emptiness extends in all directions for distances that make our solar system's dimensions seem almost cozy by comparison. If you could travel at the speed of light, it would take you over 4 years just to reach the nearest star system. To cross our entire galaxy would require 100,000 years of travel at the universe's ultimate speed limit. Yet, even our galaxy represents just one island of matter in an ocean of cosmic emptiness that extends far beyond anything we've discussed so far. The nearest major galaxy to ours, Andromeda, sits over 2.5 million light-years away. Between our galaxy and Andromeda lies a void so vast and empty that it contains perhaps a few dozen small satellite galaxies, scattered across distances that would take light millions of years to traverse. This cosmic perspective transforms our understanding of what it means to ask how big our solar system really is. The question isn't just about measuring distances within our local stellar neighborhood. It's about understanding our place in a hierarchy of cosmic structures that extends from planetary orbits to galactic clusters to the largest known structures in the observable universe. At each level of this cosmic hierarchy, the scales involved become more difficult to comprehend. Planetary systems span light hours to light years. Galaxies span tens of thousands of light years. Galaxy clusters span millions of light years. The largest cosmic structures, great walls of galaxies separated by enormous voids, can extend across hundreds of millions of light years. Our solar system, impressive as its dimensions may seem, represents just the first tiny step up this ladder of cosmic scale. We are inhabitants of what amounts to a single room in a house that sits on a street in a neighborhood that's part of a city, that exists within a county, that belongs to a state in a country, on a continent of a planet, in a solar system that's one of billions, in a galaxy that's one of trillions, in an observable universe that might itself be just a tiny fraction of a larger multiverse, whose true extent we can't even begin to imagine. This progression of scales reveals something profound about the nature of size and distance in our universe. At each level, the structures that seemed impossibly large at the previous level become almost negligibly small. Our solar system, which spans light years and contains trillions of objects, becomes a barely detectable speck when viewed from the perspective of our galaxy. Our galaxy, containing hundreds of billions of stars, becomes invisible when viewed from the distance of far galactic clusters. Yet paradoxically, this cosmic perspective also highlights just how extraordinary our local neighborhood really is. In all the vast emptiness of intergalactic space, across distances so large they challenge the very meaning of the word distance, complex structures like our solar system are incredibly rare and precious oases of organized matter and energy. The fact that gravity can create and maintain such intricate cosmic architectures across such enormous scales is itself a kind of miracle. The delicate gravitational ballet that keeps planets in stable orbits, that maintains the structure of asteroid belts and comet clouds, that allows moons to orbit planets while planets orbit stars, while star systems orbit galactic centers, requires a kind of cosmic fine-tuning that seems almost impossibly precise. Change the strength of gravity by even a small amount, and stable planetary orbits become impossible. Make space expand faster, and galaxies never form in the first place. Alter the properties of matter in subtle ways, and stars can't ignite, or planets can't solidify. The universe we observe, with its hierarchy of structures extending from subatomic particles to galactic superclusters, exists within an incredibly narrow range of physical parameters that allow complexity and structure to emerge from primordial chaos. Our solar system represents one successful solution to the challenge of creating stable, long-lived structures in a universe governed by the competing forces of gravity and expansion, attraction and motion, order and entropy. The fact that this solution has persisted for over 4.5 billion years, allowing time for planets to cool, atmospheres to develop, and life to emerge and evolve, makes our cosmic neighborhood not just large, but also incredibly precious. Every measurement of distance within our solar system, every calculation of orbital periods and gravitational influences, every discovery of new objects in the outer darkness adds another piece to our understanding of how this remarkable system manages to maintain its stability and complexity across such vast scales of space and time. The question of how big our solar system really is thus becomes not just a matter of astronomical measurement, but a window into the fundamental nature of cosmic organization itself. We're not just measuring empty space between isolated objects. We're mapping the architecture of gravitational relationships that bind our cosmic neighborhood together and allow it to function as an integrated system despite the enormous distances involved. This architectural perspective reveals that size alone doesn't capture the full significance of our solar system's dimensions. What matters isn't just how far objects are from each other, but how these distances enable the complex interactions that make our cosmic neighborhood a living, dynamic system, rather than just a collection of isolated worlds drifting through empty space. The enormous distances between planets allow them to maintain stable, independent orbits without interfering destructively with each other. The vast extent of the Oort Cloud provides a reservoir of cometary materials that occasionally refresh the inner solar system with water and organic compounds. The subtle gravitational influences that operate across billions of miles help maintain long-term stability while allowing for gradual evolutionary changes that prevent the system from becoming completely static and lifeless. In this sense, our solar system's enormous size isn't just an interesting astronomical fact. It's an essential feature that makes possible everything from stable climates to the gradual delivery of life-supporting materials to the long-term habitability of worlds like Earth. The scale that initially seems to separate and isolate objects actually enables the connections and interactions that make our cosmic neighborhood a unified, functioning system. Understanding this interconnected nature of our solar system's vast architecture leads us to perhaps the most mind-bending realization yet. When we think about communication and travel across these cosmic distances, we're not just dealing with practical challenges. We're confronting fundamental limitations imposed by the very structure of space-time itself. Consider what it would mean to have a conversation with someone living on Neptune. Even traveling at the speed of light, the absolute fastest anything can move in our universe, your words would take over 4 hours to reach them. Their response would take another 4 hours to return to you. What we think of as a simple back-and-forth exchange would stretch across an entire day, assuming both parties responded immediately upon receiving each message. But this communication delay is nothing compared to what we'd face trying to talk to inhabitants of the outer Oort Cloud. A radio message sent to the edge of our solar system would take over 2 years to arrive at its destination. The return message would take another 2 years to come back. You could ask someone a question when you're 20 years old and not receive their answer until you're 24. Entire relationships, careers, and life chapters could unfold in the time it takes for a single exchange of ideas across our solar system's true diameter. This temporal stretching of communication reveals something profound about the nature of existence in a cosmic system this large. Different regions of our solar system don't just exist at different distances from each other. They exist in different temporal relationships with the rest of the system. The outer Oort Cloud lives in a fundamentally different kind of present than we do here on Earth. When we observe Jupiter through a telescope, we're seeing it as it was 43 minutes ago. When we look at the most distant confirmed objects in our solar system, we're seeing them as they were hours or even days ago. In a very real sense, our solar system doesn't have a unified, present moment. Instead, it exists as a collection of overlapping temporal zones, each experiencing its own, slightly different version of now. This temporal complexity becomes even more fascinating when you consider how it affects the very concept of simultaneous events. If something dramatic happened to the Sun right now, Earth wouldn't know about it for 8 minutes. Mars might not find out for up to 24 minutes. Jupiter would remain unaware for nearly 3/4 of an hour. The outer planets could continue their normal existence for several hours before the effects reached them. In that sense, our solar system doesn't just span incredible distances in space. It spans incredible distances in time as well. The same event propagates outward through our cosmic neighborhood, like ripples on a vast pond, reaching different locations at different moments, creating a cascade of cause and effect that can stretch across days or even weeks. But the temporal challenges of our solar system's scale pale in comparison to the navigational complexity of actually traveling between these distant worlds. When mission planners calculate trajectories for spacecraft, they're not just plotting routes through three-dimensional space. They're choreographing journeys through four-dimensional space-time, timing launches and course corrections to intercept moving targets across billions of miles of constantly shifting cosmic terrain. Consider the challenge of sending a spacecraft to Jupiter. You can't simply aim at where Jupiter appears to be in the sky and fire your rockets. By the time your spacecraft crosses the vast distance between Earth and Jupiter's orbital path, Jupiter will have moved hundreds of millions of miles from its starting position. Instead, you have to aim at where Jupiter will be when your spacecraft finally arrives, calculating the intersection of two moving objects across distances so large that tiny errors in initial trajectory can result in missing your target by millions of miles. This problem becomes exponentially more complex as you venture into the outer solar system. A mission to Neptune requires predicting where that distant world will be, not in months, but in years or even decades. The spacecraft must be launched on a trajectory that accounts for the gravitational influences of multiple planets, the subtle effects of solar wind pressure, and even the tiny but measurable impact of Einstein's relativistic corrections to classical orbital mechanics. The mathematical precision required for these calculations pushes human knowledge to its very limits. Mission planners must account for gravitational influences so subtle they wouldn't be noticeable over distances of mere millions of miles, but become crucial when accumulated over billions of miles and years of travel time. They must predict the future positions of planets with an accuracy that would be impressive, even if those planets were sitting still, much less while they're racing through space at tens of thousands of miles per hour. Yet somehow, we've managed to master this cosmic choreography well enough to send robotic explorers to every major planet in our solar system. We've landed on Mars, orbited Jupiter, flown through Saturn's rings, and sent spacecraft beyond the edge of the heliosphere into interstellar space. Each of these achievements represents a triumph of human mathematics and engineering over the seemingly impossible challenges posed by our solar system's enormous scale. The Voyager missions provide perhaps the most stunning example of this navigational mastery. Launched in the late 1970s, these spacecraft were designed to take advantage of a rare alignment of the outer planets that occurs only once every 175 years. By carefully timing their trajectories, mission planners were able to use gravitational assists from Jupiter and Saturn to fling these robotic explorers toward Uranus and Neptune, and eventually into interstellar space itself. The precision required for these gravitational slingshots is almost incomprehensible. The spacecraft had to arrive at exactly the right location relative to each planet at exactly the right moment to receive the proper gravitational kick toward their next destination. Miss the target by even a few hundred miles or a few minutes, and the entire mission trajectory would be ruined. Yet both Voyager spacecraft executed these cosmic billiard shots flawlessly, using the gravitational fields of giant planets as stepping stones across the outer solar system. They transformed what should have been impossible journeys requiring decades of continuous rocket thrust into elegant gravitational dances that carried them to the edge of our solar system and beyond, using only the initial push provided by their launch rockets. The success of missions like Voyager reveals something remarkable about the hidden order underlying our solar system's apparent chaos. Despite the enormous distances, complex orbital mechanics, and multiple gravitational influences at play, our cosmic neighborhood operates according to mathematical principles precise enough to allow for incredibly accurate long-term predictions. The same laws of physics that govern the motion of a thrown ball here on Earth also determine the paths of spacecraft across billions of miles of interplanetary space. This mathematical predictability becomes even more impressive when you consider the timescales involved. The orbital mechanics calculations that guided Voyager's trajectory were based on observations and theories developed over centuries of astronomical research. Scientists in the 1700s and 1800s, working with nothing more than telescopes and pencil and paper calculations, laid the mathematical groundwork that made these 21st century space missions possible. Isaac Newton's law of universal gravitation, formulated in the 1600s, provides the fundamental framework we still use to navigate spacecraft across the solar system. Johannes Kepler's laws of planetary motion, derived from careful observations in the early 1600s, continued to describe the elliptical orbits followed by both natural bodies and artificial spacecraft. The mathematical tools developed by these scientific pioneers centuries ago remain adequate for the most sophisticated space missions we can currently imagine. This continuity between historical astronomy and modern space exploration reveals something profound about the nature of scientific knowledge and the structure of our universe. The same mathematical relationships that ancient astronomers discerned by carefully tracking the positions of wandering stars continue to govern the motion of high-tech robotic explorers racing through the outer darkness of our solar system. But our growing mastery of solar system navigation has also revealed just how much we still don't know about our cosmic neighborhood's true extent and complexity. Each successful mission to the outer planets has discovered phenomena that previous theories couldn't predict. From the active volcanism on Jupiter's moon Io, to the methane lakes on Saturn's moon Titan, to the geysers of water ice erupting from the south pole of Saturn's moon Enceladus. These discoveries remind us that our solar system isn't just large, it's also incredibly diverse, containing environments and processes that challenge our understanding of planetary science. The same gravitational forces that create the elegant orbital mechanics we've learned to navigate also drive complex geological processes on worlds billions of miles from the sun. Tidal heating from gravitational interactions can keep subsurface oceans liquid on moons so distant that sunlight provides virtually no warmth. Atmospheric dynamics can create weather patterns that persist for centuries on planets where seasons last for decades. This diversity exists because of, not despite, our solar system's enormous scale. The vast distances between objects allow each world to develop its own unique characteristics without interference from its neighbors. Unlike Earth, where global circulation patterns eventually mix and homogenize atmospheric and oceanic conditions, the worlds of our outer solar system exist in splendid isolation, free to evolve their own distinctive environments over billions of years. Mars develops a thin carbon dioxide atmosphere and experiences dust storms that can engulf the entire planet for months. Venus creates a crushing greenhouse effect that melts lead and produces sulfuric acid rain. Jupiter maintains a storm system larger than our entire planet that has been raging continuously for centuries. Each of these environments represents a different, solution to the challenge of planetary evolution made possible by the cosmic isolation that our solar system's enormous distances provide. But perhaps the most remarkable aspect of this diversity is how it extends even to objects we once thought were simple and uniform. The asteroid belt, for instance, was originally conceived as a relatively homogeneous collection of rocky debris left over from planetary formation. Detailed study has revealed it to be an incredibly complex region, containing objects with wildly different compositions, structures, and histories. Some asteroids are solid chunks of metal and rock, remnants of the cores of shattered planetesimals. Others are loose collections of rubble, held together by their own weak gravity, so fragile that a strong push could scatter them like cosmic dust. Still others appear to be extinct comets, their volatile materials long since boiled away by repeated passages near the sun, leaving behind only dark, carbonaceous skeletons. Ceres, the largest object in the asteroid belt, has turned out to be complex enough to qualify as a dwarf planet in its own right. Recent spacecraft missions have revealed that Ceres has a differentiated interior, with a possible subsurface ocean, making it yet another potentially habitable world in our solar system. What we once dismissed as cosmic rubble has proven to contain environments that might rival those of the moons of Jupiter and Saturn in their potential for harboring life. This pattern of increasing complexity with increasing exploration extends throughout our solar system. The more closely we examine any region of our cosmic neighborhood, the more intricate and fascinating it becomes. The Kuiper Belt has revealed itself to be populated by objects following bizarrely complex orbital patterns that hint at gravitational influences we don't yet understand. The scattered disk beyond Neptune contains worlds like Eris that challenge our very definitions of what constitutes a planet. Even the space between planets, once thought to be essentially empty, has proven to be filled with dust, charged particles, and magnetic field structures that create invisible highways and barriers throughout our solar system. Each of these discoveries adds another layer of complexity to our understanding of what it means to measure our solar system's true size. We're not just dealing with simple distances between isolated objects floating in empty space. We're mapping the architecture of an incredibly intricate system where every component influences every other component, across vast distances through mechanisms we're only beginning to understand. The magnetic field generated by Jupiter's rapid rotation, for instance, creates a magnetosphere so large that it would be visible to the naked eye from Earth if we could somehow see magnetic field lines. This invisible bubble extends millions of miles around Jupiter, trapping charged particles from the solar wind and creating radiation belts so intense they can damage spacecraft electronics. The interaction between Jupiter's magnetosphere and the thin atmospheres of its moons creates auroras on worlds billions of miles from the sun. Saturn's rings, those elegant bands of ice and rock that have captivated observers for centuries, turn out to be maintained by incredibly complex gravitational relationships between the planet's dozens of moons. Some moons shepherd ring particles into narrow bands, while others create gaps by sweeping up material in their orbital paths. The entire ring system exists in a delicate gravitational balance that spans hundreds of thousands of miles, yet can be disrupted by objects as small as houses. Even our sun, the gravitational anchor that holds our entire solar system together, reaches across billions of miles through mechanisms more subtle than simple gravitational attraction. The solar wind, a stream of charged particles flowing outward from our star at speeds of several hundred miles per second, creates a dynamic pressure that affects the orbits of comets, pushes against the magnetospheres of planets, and ultimately defines the boundary between our solar system and interstellar space. This solar wind pressure creates the heliosphere, a vast bubble of solar influence that extends far beyond the orbit of Pluto. The boundary where this bubble meets the interstellar medium, called the heliopause, represents one possible definition of our solar system's edge. But this boundary isn't fixed or static. It expands and contracts based on variations in solar activity and changes in the density of the interstellar medium through which our solar system is moving. The Voyager spacecraft, our most distant robotic ambassadors, have now crossed this boundary and are sending back humanity's first direct measurements of the interstellar environment. What they found is that the transition from the solar system to interstellar space isn't sharp or sudden. Instead, it's a gradual shift through multiple boundary layers, each with its own characteristic properties and dynamics. This discovery has profound implications for how we think about our solar system's true extent. Rather than having a clear edge like the surface of a planet, our cosmic neighborhood seems to fade gradually into the larger galactic environment through a series of transition zones that extend across multiple astronomical units. The question of where our solar system ends and interstellar space begins becomes less about identifying a specific boundary and more about understanding a complex set of overlapping zones of influence. But even as we grapple with these boundary questions, new discoveries continue to push our understanding of solar system scale in unexpected directions. The detection of interstellar objects passing through our solar system, like the asteroid Oumuamua and the comet Borisov, reminds us that our cosmic neighborhood isn't isolated from the rest of the galaxy. These visitors from other star systems carry with them information about planetary formation processes in alien solar systems, providing glimpses of how other stellar families compare to our own. The fact that we can detect and study these interstellar interlopers reveals just how sophisticated our observational capabilities have become. Objects smaller than football fields, moving at tens of miles per second, can now be spotted and tracked as they race through our solar system on trajectories that will carry them back into the galactic darkness. These detections represent an entirely new frontier in astronomy, one that promises to reveal the diversity of planetary systems throughout our galaxy. But perhaps the most mind-expanding aspect of our solar system's scale is how it prepares us to contemplate even larger cosmic structures. The distances that seem so impossibly vast within our solar system become almost intimate when viewed from the perspective of interstellar space. Our entire cosmic neighborhood, from the Sun to the outer edge of the Oort Cloud, occupies only the tiniest fraction of the space between neighboring star systems. If our solar system were shrunk down to the size of a coin, the nearest star would still be over a mile away. The distances that challenge our ability to comprehend within our solar system become negligible when measured against the true scale of our galaxy. Yet, this cosmic perspective also highlights just how extraordinary it is that stable, complex systems like our solar system can exist at all in a universe dominated by such vast, empty spaces. The gravitational forces that bind our cosmic neighborhood together operate across distances so large that their effects become almost impossibly subtle, yet somehow remain strong enough to maintain stable orbits for billions of years. The delicate balance between gravitational attraction and orbital motion that keeps planets in stable paths requires a kind of cosmic fine-tuning that seems almost miraculous when contemplated from the perspective of galactic distances. This balance becomes even more remarkable when you consider that it must be maintained not just across space, but across time as well. Our solar system has existed, in roughly its current configuration, for over 4.5 billion years, during which time our Sun has traveled completely around the galaxy, roughly 20 times. Throughout this cosmic journey, passing close to other star systems, threading through spiral arms dense with stellar neighbors, our solar system has somehow maintained its structural integrity and continued to provide stable conditions for the evolution of life. The fact that complex, long-lived structures like our solar system can exist and persist in a universe characterized by such enormous scales of distance and time speaks to deep principles of cosmic organization that we're only beginning to understand. The same mathematical relationships that govern the motion of planets around our sun also determine the orbits of star systems around galactic centers and galaxies around the centers of galaxy clusters. This hierarchy of cosmic structures, each level bound together by gravitational forces operating across increasingly vast distances, suggests that the principles we observe in our solar system might be universal features of how matter organizes itself in the universe. The techniques we've developed for understanding and navigating our cosmic neighborhood might provide insights into the structure and dynamics of much larger systems, extending far beyond our local galactic environment. As we continue to probe the outer reaches of our solar system and develop more sophisticated techniques for detecting and studying distant objects, we're not just mapping our local cosmic territory. We're developing the conceptual and technological tools needed to understand our place in the vast hierarchy of cosmic structures that extends from planetary systems to galactic superclusters. The question of how big our solar system really is thus becomes a gateway to even grander questions about the scale and structure of the universe itself. Each measurement of distance within our cosmic neighborhood, each discovery of a new object in the outer darkness, each successful navigation of a spacecraft across billions of miles of space adds another piece to our understanding of how complex systems can emerge and persist across the mind-bending scales of cosmic space and time. In probing the true dimensions of our solar system, we're not just satisfying scientific curiosity about our local environment. We're taking the first steps toward understanding our place in a universe whose true scale and complexity may forever exceed our ability to fully comprehend, yet somehow remains governed by mathematical principles elegant enough for finite minds like ours to discover and appreciate. And here's where our journey through cosmic distances takes perhaps its most mind-bending turn yet. Because when we truly grasp the scale of our solar system, we begin to understand something that challenges every assumption we have about speed, distance, and what it means to be fast in the cosmic arena. You see, we live in a world where speed has very specific meanings. A car traveling 60 miles per hour seems reasonably fast. A jet aircraft cruising at 600 miles per hour feels impressively rapid. Even our fastest bullet trains, racing along at 200 miles per hour, give us a visceral sense of velocity that we can relate to our everyday experience. But here's what will absolutely shatter your perception of speed. Right now, as you sit there absorbing these cosmic dimensions, you are moving through space at velocities that make every human-made vehicle look like it's standing perfectly still. And I'm not just talking about Earth's rotation, though that alone carries you eastward at over 1,000 miles per hour, if you happen to be near the equator. No, we're talking about something far more spectacular. Our entire planet is hurtling around the sun at roughly 67,000 miles per hour. That's fast enough to circle the entire Earth in about 22 minutes. Yet, even this breakneck orbital velocity, impressive as it sounds, represents just the beginning of our cosmic speed journey. Because our sun, dragging along its entire family of planets, moons, asteroids, and comets, is racing through the Milky Way galaxy at approximately 500,000 miles per hour. At this speed, You could travel from New York to Los Angeles in about 30 seconds. You could circle the Earth's equator in roughly 3 minutes. Yet, this incredible velocity carries us on a galactic orbit so vast that it takes our solar system roughly 225 million years to complete just one lap around our galaxy's center. Think about that timeline for a moment. The last time our solar system was in this exact position, relative to the galactic center, the most advanced life forms on Earth were primitive marine creatures just beginning to venture onto land. Dinosaurs wouldn't appear for another 100 million years. The next time we complete this cosmic circuit, our sun will be noticeably older and dimmer, and the face of our planet will have been reshaped by geological and evolutionary forces we can barely imagine. But even our galaxy's stately rotation through space doesn't represent the end of our cosmic velocity stack. Our entire galaxy, along with its neighbors in what astronomers call the local group, is racing through the universe toward an eventual collision with the Andromeda Galaxy. This intergalactic approach occurs at speeds exceeding 250,000 miles per hour, fast enough to cross the continental United States in about 6 minutes. When that cosmic collision finally occurs, roughly 4.5 billion years from now, the gravitational chaos will completely reshape both galaxies, potentially flinging our solar system into entirely new regions of space, or ejecting it altogether into the lonely depths of the intergalactic void. The very structure of our cosmic neighborhood could be fundamentally altered by gravitational forces operating across distances that dwarf even our solar system's impressive dimensions. And still, we haven't reached the ultimate expression of cosmic motion. The entire local group of galaxies, including our Milky Way and Andromeda, participates in the expansion of the universe itself. Space itself is stretching, carrying galaxy clusters away from each other at velocities that increase with distance. The most distant galaxies we can observe are receding from us at speeds approaching the velocity of light, not because they're moving that fast through space, but because space itself is expanding between us. This cosmic expansion affects even our solar system in subtle but measurable ways. Over unimaginably long timescales, the expansion of space itself will gradually weaken our sun's gravitational hold on its most distant subjects. Objects at the very edge of the Oort Cloud are slowly but inexorably drifting away from our star, stolen not by the gravity of passing objects, but by the fundamental expansion of the universe itself. This process operates so slowly that it would take trillions of years to have any noticeable effect on our solar system structure. But the fact that it's happening at all reveals something profound about the dynamic nature of cosmic architecture. Our solar system isn't a static structure frozen in space and time. It's a dynamic, evolving entity that responds to forces operating across multiple scales of distance and duration. But here's what makes these cosmic velocities truly mind-melting when we consider them in the context of solar system distances. Despite racing through space at speeds that make our fastest rockets look like they're crawling, the objects in our cosmic neighborhood maintain their relative positions with remarkable stability across billions of years. Jupiter has been following roughly the same orbital path for over 4.5 billion years, despite the fact that it's simultaneously participating in our solar system's galactic orbit, our galaxy's motion through the local group, and the universe's expansion. The gravitational relationships that maintain planetary orbits operate with such precision that they can overcome the chaotic influences of our participation in multiple cosmic motions operating across vastly different scales. This stability in the face of cosmic chaos becomes even more remarkable When you consider the mathematical complexity involved in maintaining orbital relationships across such enormous distances while participating in multiple layers of cosmic motion, every object in our solar system must somehow balance its gravitational relationship with the Sun against the subtle influences of galactic tides, the gravitational effects of passing stars, and even the weak but persistent influence of cosmic expansion. The fact that these delicate gravitational balances can persist across billions of years of cosmic evolution suggests that our solar system represents something truly extraordinary in the universe. We're not just dealing with a large collection of objects held together by gravity. We're observing a stable, long-lived structure that has somehow learned to dance with forces operating across scales, from planetary orbits to cosmic expansion. This cosmic choreography becomes even more fascinating when you consider how it affects our attempts to measure and navigate within our solar system. When we send spacecraft to distant planets, we're not just calculating trajectories through three-dimensional space. We're plotting courses through a four-dimensional space-time that's simultaneously rotating around our galactic center, racing toward Andromeda, and participating in the expansion of the universe itself. The mathematical precision required for these calculations pushes human knowledge to its absolute limits. Mission planners must account not only for the gravitational influences of planets and moons, but also for the subtle effects of our solar system's motion through the galaxy, the influence of dark matter halos, and even the tiny but measurable corrections imposed by Einstein's theories of relativity. Yet somehow, we've mastered this cosmic navigation well enough to send robotic explorers throughout our solar system with extraordinary precision. We can predict where Jupiter will be in a decade with accuracy measured in kilometers, despite the fact that Jupiter will have traveled billions of miles through galactic space during that time while participating in multiple layers of cosmic motion. This navigational mastery reveals something profound about the mathematical elegance underlying cosmic motion. Despite the apparent complexity of multiple overlapping velocities and gravitational influences, the universe operates according to principles precise enough to allow for incredibly accurate, long-term predictions across mind-bending scales of distance and time. But perhaps the most humbling aspect of contemplating our solar system's true scale is how it reveals the extraordinary rarity and preciousness of the stable conditions that have allowed complex structures like planetary systems to form and persist. In a universe characterized by such enormous distances, such tremendous velocities, and such powerful forces, the existence of delicate gravitational relationships capable of maintaining stable orbits for billions of years seems almost miraculous. Consider the incredible chain of cosmic circumstances that had to align perfectly for our solar system to exist in its current form. Our location in the galaxy had to be just right, far enough from the chaotic galactic center to avoid disruptive gravitational influences, but not so far out in the galactic suburbs that we lacked access to the heavy elements created by previous generations of stars. Our sun had to form with just the right mass to provide stable energy output for billions of years. The early gravitational interactions between forming planets had to settle into stable configurations that could persist despite the ongoing chaos of cosmic evolution. Each of these requirements represents a kind of cosmic lottery ticket, and our solar system somehow managed to win every single drawing. The mathematical probability of all these factors aligning perfectly seems vanishingly small. Yet here we are, living proof that such extraordinary cosmic arrangements not only can exist, but can persist long enough for complex chemistry to evolve into biology, and biology to evolve into consciousness, capable of contemplating its own cosmic origins. This perspective transforms our understanding of what it means to ask how big our solar system really is. We're not just measuring empty space between isolated objects. We're mapping the architecture of a cosmic miracle, a stable island of organized matter and energy that has somehow learned to maintain its structure across scales of distance and time that challenge the very limits of human comprehension. Every measurement we make, every spacecraft we navigate across billions of miles, every calculation of orbital mechanics across cosmic timescales represents not just a scientific achievement, but a kind of cosmic archaeology. We're uncovering the hidden relationships and delicate balances that allow our extraordinary solar system to exist and persist in a universe that seems designed to tear such structures apart. And as we continue to probe the outer reaches of our cosmic neighborhood, discovering new objects in the distant darkness, and mapping the subtle gravitational influences that shape their orbits, we're not just expanding our knowledge of local cosmic geography. We're developing a deeper appreciation for the remarkable rarity and precious fragility of the stable cosmic structures that make our existence possible. The question of our solar system's true size thus becomes a meditation on the extraordinary nature of cosmic organization itself. In measuring the distances between worlds, we're really measuring the spaces between miracles, mapping the architecture of cosmic improbability that somehow conspired to create a corner of the universe where matter could organize itself into planets and moons and asteroid belts and comet clouds, and ultimately into the complex arrangements of atoms we call life. Every new discovery in the outer solar system, every successful navigation of spacecraft across interplanetary distances, every precise prediction of planetary positions across cosmic timescales adds another verse to the most remarkable story ever told. The story of how, in a universe characterized by chaos, expansion, and destruction on the largest scales, delicate gravitational relationships can create and maintain islands of stability, beauty, and complexity across distances so vast they defy human intuition. We are temporary arrangements of stellar debris that have somehow achieved the capacity to contemplate the cosmic architecture that contains us. In measuring our solar system's true dimensions, we're really measuring the scale of the miracle that made our existence possible. And that measurement, however precise our instruments become, however far our spacecraft travel, however deep our mathematical understanding grows, will always point towards something larger and more wonderful than any mere collection of numbers could ever capture. The true size of our solar system isn't just about distance. It's about the incredible fact that in a universe of such unimaginable scale, such tremendous forces, such chaotic motion, something as delicate and beautiful and improbably stable as our cosmic neighborhood could exist at all, and, having achieved existence, could persist long enough for some of its matter to wake up and wonder about its own origins. In that wondering, in that questioning, in that persistent human drive to measure and understand and explore, we find perhaps the most remarkable dimension of our solar system's true scale. Not just its physical extent across light years of space, but its capacity to give rise to minds capable of contemplating infinity itself. But perhaps the most staggering realization about our solar system's true dimensions comes when we consider what lies in the spaces between these cosmic landmarks. You see, when most people imagine our solar system, they picture the familiar diagram from textbooks: neat circles representing planetary orbits, evenly spaced like ripples on a pond. But this sanitized version completely fails to capture the mind-bending reality of what actually exists in those seemingly empty regions. The space between Mars and Jupiter, for instance, isn't just a gap waiting to be crossed. It's home to hundreds of thousands of asteroids, each following its own unique orbital dance around the Sun. Some of these rocky fragments are larger than mountains, while others are no bigger than boulders. They tumble through the darkness in a cosmic ballet so complex that no human mind could track all their interactions simultaneously. But here's what will truly scramble your understanding of scale. The asteroid belt, containing all these hundreds of thousands of objects, is so vast that if you were standing on one asteroid, the chances of seeing another asteroid with the naked eye would be virtually zero. The average distance between asteroids is over 1 million miles. You could fire a spacecraft randomly into the asteroid belt, and the odds of hitting anything would be astronomically small. This emptiness, with an apparent fullness, extends throughout our entire solar system. The space between Earth and Mars, which seems so manageable when drawn on paper, actually contains a volume roughly equivalent to 8 billion Earth-sized spheres. The gap between Jupiter and Saturn could hold over 20 billion Earth-sized objects without any of them touching. We're dealing with emptiness on a scale that makes terrestrial concepts of distance seem quaint. Yet within these vast empty regions, incredibly subtle forces are constantly at work, shaping and reshaping the architecture of our cosmic neighborhood. Gravitational resonances create invisible patterns that determine where objects can maintain stable orbits and where they'll be swept away by planetary influences. The solar wind carves out magnetic highways and barriers that affect the motion of charged particles across billions of miles. Even more fascinating are the Trojan asteroids, cosmic hitchhikers that share Jupiter's orbit around the Sun, while maintaining positions roughly 60 degrees ahead of and behind the giant planet. These objects demonstrate how gravitational relationships can create stability across enormous distances, allowing small bodies to maintain fixed positions relative to much larger objects, despite the complex dance of forces operating throughout the solar system. The discovery of these Trojan populations has revealed that our solar system contains gravitational sweet spots, regions where the competing influences of different massive bodies create zones of stability that can trap objects for billions of years. Jupiter alone has over 7,000 known Trojans, but recent surveys suggest there may be hundreds of thousands more, too small or distant for us to detect. But Jupiter's Trojans represent just one example of how our solar system's enormous scale creates opportunities for gravitational complexity that wouldn't exist in a smaller, more compact arrangement. Neptune has its own population of Trojan companions. Mars hosts a small collection of co-orbital asteroids. Even Earth shares its orbital path with a few tiny companions that follow complex trajectories around our planet's Lagrange points. These gravitational relationships reveal something profound about the hidden architecture of our solar system. What appears from a distance to be a simple arrangement of planets orbiting a star actually contains layer upon layer of subtle interactions and complex dynamics that operate across the full range of solar system distances. Consider the Hildas, a group of asteroids that maintain a precise 3-to-2 orbital resonance with Jupiter. These objects complete exactly 3 orbits around the Sun for every 2 that Jupiter completes. A mathematical relationship so precise that it's maintained across millions of years, despite the gravitational perturbations from other planets. The Hildas occupy a region of space larger than the orbit of Mars, yet they move in such perfect synchronization with Jupiter that their relative positions remain essentially unchanged across geological timescales. This kind of gravitational choreography extends throughout the outer solar system as well. The Kuiper Belt contains families of objects locked in various resonances with Neptune. creating a complex structure of populated and empty zones that reflects billions of years of gravitational sculpting. Some regions are packed with icy bodies, while others remain virtually empty due to orbital instabilities that eject objects over cosmic time. The precision of these gravitational relationships becomes even more remarkable when you consider the distances involved. Neptune's influence on Kuiper Belt objects operates across billions of miles, yet it's strong enough to maintain mathematical relationships accurate to fractions of a percent over millions of orbital periods. It's like having a conductor directing a cosmic orchestra, where the musicians are scattered across light hours of space, yet somehow maintaining perfect synchronization. But perhaps the most mind-expanding aspect of our solar system's true scale emerges when we consider how these vast distances affect our very perception of time itself. We've grown accustomed to thinking of simultaneity as absolute, assuming that when something happens, it happens everywhere at the same moment. But the finite speed of light, combined with our solar system's enormous dimensions, reveals that simultaneity is actually relative to position within our cosmic neighborhood. When a solar flare erupts on the sun's surface, Earth experiences its effects 8 minutes later. But Mars, depending on its orbital position, might not feel those same effects for anywhere from 12 to 24 minutes. Jupiter could remain unaware of the solar disturbance for nearly an hour. The outer planets might continue their normal existence for several hours before the effects propagate outward to their distant realms. This means that our solar system doesn't experience a unified, present moment. Instead, it exists as a collection of overlapping temporal zones, each operating on its own, slightly delayed timeline relative to solar events. A dramatic solar eruption creates a wave of cause and effect that propagates outward through our cosmic neighborhood, like ripples on a vast pond, reaching different worlds at different times and creating a cascade of responses that can stretch across days. But the temporal complexity of our solar system's scale extends far beyond simple light travel delays. The orbital periods of objects throughout our cosmic neighborhood span an incredible range, from Mercury's 88-day year to the million-year orbits of some Oort Cloud comets. This means that different regions of our solar system experience time at fundamentally different rates when measured in terms of their relationship to the Sun. An object in the inner solar system might complete hundreds of orbits during the time it takes something in the outer Oort Cloud to move through just a tiny fraction of its immense orbital path. These different temporal rhythms create a kind of cosmic polyrhythm, where various parts of our solar system are beating to completely different drums, while somehow maintaining overall structural harmony. The implications become even more staggering when you realize that this temporal diversity is precisely what allows our solar system to maintain its stability across billions of years. If everything operated on the same time scale, gravitational interactions would either quickly drive objects into collisions or eject them from the system entirely. Instead, the vast range of orbital periods creates a natural buffer against chaos, allowing temporary perturbations to average out over time, rather than building up into system-destroying instabilities. This temporal architecture reveals yet another dimension of what it means to measure our solar system's true size. We're not just dealing with static distances frozen in space. We're mapping a dynamic system where different regions operate according to different temporal rhythms, where cause and effect propagate at the speed of light across light hours of distance, where the very concept of simultaneity becomes relative to position within our cosmic neighborhood. The more deeply we probe these temporal relationships, the more we realize that our solar system's enormous scale isn't just about the space between objects. It's about the time relationships that connect distant worlds to our central star and to each other. Every measurement of distance also becomes a measurement of temporal delay. Every calculation of orbital mechanics must account for the finite speed at which forces and influences propagate across the vast emptiness of interplanetary space. This temporal dimension of solar system scale has profound implications for any future human exploration of our cosmic neighborhood. A conversation between Earth and a Mars colony would involve delays measured in minutes. Communication with explorers in the outer solar system would require the patience of geological time, with hours or days passing between question and response. But perhaps most humbling of all is the realization that these vast scales of distance and time have been operating long before humans existed and will continue long after we're gone. Our entire species represents just the briefest instant in our solar system's 4.5 billion year history. Yet in that cosmic eye blink, we've managed to develop the mathematical tools and technological capabilities needed to measure and understand the true dimensions of our cosmic home. Every successful spacecraft mission, every precise prediction of planetary positions, every discovery of new objects in the outer darkness represents a triumph of human consciousness over the seemingly impossible challenges posed by cosmic scale. We are temporary arrangements of matter that have learned to think across light years of space and billions of years of time, measuring distances so vast they challenge the very foundations of human intuition. So here we are at the end of our cosmic journey together, having traveled from your backyard all the way to the edge of everything our sun can touch. We've crossed distances so vast that light itself takes years to make the journey, explored realms where time moves differently, and discovered that our solar system isn't just big, it's a living, breathing, dynamic universe unto itself. Tonight, when you step outside and look up at those same points of light that started our adventure, you'll never see them the same way again, because now you know the truth about the cosmic ocean we're swimming in, and just how extraordinary it is that we're here at all to contemplate its infinite mystery. I wish you a very good night. I hope you had an amazing time with me here at Stellify Science. I will see you tomorrow, as always. Until then, stay curious and keep wondering. This is Stellify Science, signing off. Cheers.